Hello and welcome to our lecture on forecasting fundamentals. I'm going to divide this lecture into four parts. First, I'm going to talk about the forecasting imperative. That is, why do we go about forecasting? What are some of the basic laws of forecasting? What is the difference between strategic and tactical forecasting? And really, why is it important for us to do it? The second section, we're going to deal with forecasting approaches. We're going to look at time series forecasting models, causal forecasting models, and more qualitative approaches. Then we'll talk about the importance of measuring forecast accuracy and talk about two basic measures, mean absolute percentage error and mean forecast error. And we'll show why it's important to try to drive down forecast accuracy. To give you a little hint, there's basically a trade-off between resources we have to spend and forecast accuracy. So if we can improve the accuracy of our forecasts, in a lot of business situations, it means we can save money and reduce excess capacity requirements. Finally, I'm going to talk about the forecasting business process. At this point in the lecture, we'll have covered the different methods, we'll have dealt with the quantitative techniques, but the forecasting business process really deals with people. That is, how do we share the forecast? How do we integrate it into our daily activities? And what you'll find out in a lot of business situations, they do a great job of generating the numbers, but they don't use them correctly. So let's dive right in. Lesson 1, the forecasting imperative. First of all, forecasts are a critical input to planning at both the strategic and tactical levels. In fact, most planning activities in a business start with a forecast. At the strategic level, we're looking at long-range types of decisions. For instance, how many distribution centers do we need? How many plants? Are we going to expand our business overseas or not? These forecasts tend to cover very long periods of time with very aggregated types of data. In contrast, tactical forecasts tend to be much more detailed, covering a shorter time horizon. We might need a tactical forecast to determine how many shifts we need to schedule over the next month or two, or how much safety stock we should hold. Think about the difference here. If we're talking about how much safety stock we should hold, then we're going to have to know something about the expected demand for a specific product or family of products. And that's much different than a strategic forecast when we're looking at overall levels of business. But the point is, we need both types of forecasts because in a business we're doing planning at the strategic and the tactical level. Continuing with the forecasting imperative, think about a forecast as not only a set of numbers that we need to kick off the planning process, but think about it also as a mechanism for getting agreement and coordinating activity within the firm and across supply chain partners. To give you an example, if we want to get marketing and operations together to some sort of agreement to tie their levels of business activity, then we can start with a forecast of what we think the customer is going to do. From that forecast, marketing can plan their sales and promotions efforts. Operations and supply chain can plan their physical activity flows. But it's not only within a firm, it's across the supply chain partners as well. If we have a forecast and we're going to use that to plan our level of internal operations, then we need to share that with key suppliers as well. And if you haven't already seen that in the Genentech and Scharfenberger case, let's go back and consider it. Think about Genentech. Think how important the forecast of demand for Avastin was to determining what the level of business activity is. So if we plan for Avastin to be growing by 3 to 4 times what the current demand is over the next 10 years, not only do we have to use that to plan operations activities or at least strategic capacity, but we also have to use that to plan what we're going to do in the marketplace. In addition, think about Scharfenberger chocolate. If Scharfenberger is going to grow its production levels, then they have to make sure they have the supplies of the right types of beans in the right quality and quantities. So the forecast is an important mechanism for sharing and getting agreement across the supply chain and within the firm. And there's also major types of forecasts. Now in this class we're going to deal primarily with demand forecasts, but realize that in the real world there's not only demand forecast, but there's forecast of price and there's forecast of supply. Great example of a price forecast might be if you're an airline. One of the big concerns you have is the price of fuel. So you might look at ways to forecast where the price of fuel is going and use that to decide on what kind of purchasing strategy you're going to follow. Okay, some other considerations about forecast. First of all, you're almost guaranteed that the forecast is not going to be exactly right. So yes, they're always wrong, but that doesn't mean we don't need them. We still need to have some number to plan around and to get agreement around. It's better to have a forecast that's within plus or minus 10% of what the actual demand turns out to be than to just say, we'll wing it. Secondly, forecasts are more accurate in the near term. Now that sounds pretty obvious, but it's an important point to make. Let's go back to Genentech. The lead time on adding strategic capacity at Genentech was 5 years. That's how long it took to build a new plant. So are we as concerned about the accuracy of a 10 to 15 year forecast? Not really. We might do it, but really we have to be more accurate over the next 5 years or so, because that is the time frame in which we need to make decisions about adding strategic capacity. Furthermore, take someone like GM. GM is trying to decide the specific mix of cars to make next month or even next week, but they're not worried about the precise mix of cars 6 months or 12 months later. So we don't need to have a more accurate forecast in the long term because we have more time to react. We do need accuracy in the near term. Secondly, higher level forecasts tend to be the most accurate. For example, it's easier to plan overall demand for a product family such as toothpaste than figure out what the demands are going to be for individual product lines or at the SKU level. And for Crest, I can estimate what the overall demand for toothpaste is going to be, but if I have to develop a forecast for every different possible SKU, which means packaging, size, labeling, all that kind of stuff, it's going to be very difficult. Finally, forecasts are no substitute for calculated demand. Whenever I can calculate demand exactly, I'd rather do that than use a forecast. To give you an example, if we're going to replace all the tires in 10 buses this week, how many tires do we need? And if we look at the bus over here, if I'm counting it right, it looks like it has 6 tires, 4 in the back axle and 2 in the front. So 10 buses times 6, 60 tires. That's what I need. I don't need to forecast that number. Now let me give you an example in the real world where I saw this go awry. I was doing some work with a company that made rubber products like hoses, belts, etc. They had one group that knew exactly what the plant was going to be making during the next month, exactly how many of each type of hose and belt that it had to produce. So it could easily figure out, based on what it was going to produce, exactly what the rubber requirements were by grade and by volume. So they could have easily passed that on to the people who were purchasing the raw rubber, but they didn't. In fact, the folks purchasing the raw rubber were forecasting what the raw demand for raw rubber would be without looking at what the production schedule was. So when you went outside this plant, in the back, they literally had train cars full of the wrong grades of rubber because they weren't coordinating between production planning and purchasing. It would have been very easy to calculate exactly how much rubber they needed to support production, but they didn't do it. Go figure. Okay, so that's a little bit about the imperative of why forecasting is important. And obviously already in this course, you've seen forecasts come into play. The second lesson here is to talk about some of the different forecasting approaches out there. And so what I've done is I've developed a little bit of a decision model to decide what kind of forecasting approach you need. So the first thing you should think about in a business situation is which statement best describes the forecasting situation. Am I in a situation where I have quantitative data available? I have a history of demand, and I have a history of not only the demand, but maybe some of the factors that cause the demand. So if I have quantitative data available and I have evidence of a relationship between demand and some variable of interest, whether it's demand over time or whether it's demand as a function of something else like financial performance metrics or whatever, then I'm going to go down this branch. Alternatively, I may have a situation where there's little or no data available, and relationships between past events and future events are hard to quantify. This is going to be the situation when maybe we're launching a totally new product or service, or we're going after a completely new market segment where what we've done in the past is really hard to build off of. So if we're in a situation where there's little or no data available and the relationships between past events and future events are hard to quantify, then we're going to have to depend on qualitative forecasting methods. And there's several of these we'll talk about: life cycle analogy, consensus forecasting, and managerial judgment. But in a word, all of them require some level of judgment or building off of what we think we've seen in the past. But they're certainly not going to depend on hard numbers. If we're in a situation where we have the quantitative data available, then the question we have to ask ourselves is, does the future level of demand appear to be a function of time? Let me give you an example of where demand might look to be a function of time. Think about drugs that are used for smoking cessation to help people quit smoking. If you were to plot out the demand for these drugs, you're going to see a big bump around the January time frame because people have New Year's resolutions and they want to bring their smoking, they want to try to quit smoking. And so in that case, the demand is a function of time. At the first of every year, we see a bump in demand. Alternatively, you might see a demand pattern where there's a consistent upward or downward trend or seasonality effect. So you can see how demand is affected over time. And if that's the case, we're going to look at time series forecasting models. A few we'll talk about are moving average models, exponential smoothing, and models with seasonality adjustments. So these are all very quantitative. They assume demand is a function of time. Alternatively, we might have a situation where the future level of demand is a function of something other than time. To give you an example of how this is different, think about the dollars spent on drought relief by the government. What determines how much money they're going to spend on drought relief? It's not necessarily how much they spent last year or how much they spent the year before. It's going to be tied primarily to rainfall levels and weather conditions. So if we're trying to predict how much we need to budget for drought relief, the explanatory variable would be basically weather conditions, rainfall levels. And so that would lead us into causal forecasting methods. More precisely, what we're going to talk about here is regression analysis. So that's kind of a broad overview of the different types of forecasting approaches. So with that background, let's dive in. Let's start with some very simple time series forecasting models. So the first thing I want you to do is consider this time series here. I have 8 periods and I have the demand levels for each of those 8 periods. Now I'm purposely not telling you what the periods are, whether they're days, weeks, or months, and I'm not telling you what the product is. Just look at that time series for a second. Now suppose I asked you to come up with a forecast for period 9. What would you say? Chances are you're going to come up with some number like 10 or 11 or maybe 12, but you're certainly not going to come up with a forecast of 1 or 50. What you've done in your head is very likely looked at this demand pattern, kind of took an average of it, maybe you put a little bit more emphasis on these last few periods than earlier ones. So you're going to come up with something that looks reasonable given the demand pattern you've seen over the last 8 periods. And that's what time series models do. So I want to talk about some of the different components of a time series model that we have to think about. This is an example of a time series with randomness. So if we look at this, we can see that there seems to be some average demand with some noise around it. Why do we know that's noise? Well, we don't necessarily know it's noise, but it looks to be a random pattern. There's ups and downs without any particular rhyme or reason to why that happens. Now, what if I showed you this time series? Okay, now what you see is there's a definite underlying demand that tends to be going up over time. And yet, there's some randomness around that, and there's also some seasonality effects. There tends to be a dip in demand around December of each year. This is an example of a relatively complex time series. There's randomness because there seems to be some bumpiness in it. There's definitely an upward trend, but there's also seasonality. Now here's the kicker. As an individual, you can look at that with your eyes and see those different components, but we have to find a model capable of doing that as well, differentiating between trend and randomness. differentiating between seasonality and true underlying changes in demand. And so that's going to be our challenge with time series models. The objective of time series model then is to develop a forecast that takes into consideration the effects of randomness, trends, and seasonality and does it in a rational, objective way and can do it over and over and over again without a lot of human intervention. The very simplest time series models you see out there are moving average models, and even the most expensive ERP system has these types of models in it. Moving average models can cover different numbers of periods. They can have weighting on different past observations, but I'm just going to talk about a simple one here. Let's suppose we have a 2-period moving average model. So the way we're going to forecast then for period 3 is to take an average of the last 2 periods of demand. That's what we mean by a 2-period moving average. So the 2-period moving average forecast for period 3, we're going to take 12 and 15, take the average of those, and it's going to turn out to be 13.5. And you can see that right here. Now, when we get ready to forecast for period 4, we take the average of demand for periods 2 and 3. That's what we mean by the moving part of the forecast model. So the average of 15 and 11 turns out to be 13. When we end up forecasting for period 10, we take the average of periods 3 and 4, which are 11 and 9 respectively, and 10. And so you can see how the model moves along in time, responding to what the actual demand numbers were. Now, to see how the model behaves, it's sometimes better to look at it graphically. So I'm going to take these same demand numbers and same forecast numbers and just plot them out. And you get something like this. The blue line represents the actual demand. The purple line represents the forecast. And what do you notice? Well, one of the things you notice is that the forecast is always in between the extremes of the demand, and that's because it's an average. It's based on 2 observations. Furthermore, you see there's a little bit of a lag to it. Demand's up here, forecast for the next period's here, demand starts to come down, the forecast comes down, but not all the way. Demand continues to come down, forecast model starts to come down a little bit quicker. When the demand starts to go up, the forecast model starts to go up. So if you want to think about it this way, the model's not only smoothing out the randomness in the data, but it's reacting rationally to changes in the demand. It's trying to figure out where the underlying demand pattern is. And it doesn't really overreact to any individual observation. So it's a very simple model. Now there's another example of a moving average model called exponential smoothing. And this model is a little bit more sophisticated, but let me walk through the idea here. It looks more difficult than it really is. This is a popular variation of a weighted moving average model, and it really just needs 3 numbers to develop a forecast. So if I'm trying to develop a forecast for the next time period, then I have to know what the actual demand for the current time period is, the forecast for the current period, and I have to have a smoothing weight that tells me how much weight I'm going to put on the actual demand in the current period and our current forecast. And we'll talk about how that weight works in a moment. But here's what the forecast model looks like. The forecast for period T plus 1, let's say that's the forecast for December, is going to be based on the demand in November, period T, and the forecast in November, F sub T. Alpha is between 0 and 1. So if alpha was, for instance, 0.6, I'd take 0.6 times the actual demand in November and 1 minus 0.6 or 0.4 times the forecast for November. So you notice this is the weight on the actual demand. This is the weight on the forecast. They always add up to 1. So if I weight one heavier than the other, I get a different weighting on this average. If alpha is 0.5, I'd have the same weight on actual demand in November and the actual forecast in November. So we'll talk about in a moment why we pick particular alpha values. But really, if you think about it then, if we're forecasting for December, F sub T plus 1, it's simply some kind of weighted average of what our actual demand was in November and our forecast in November. So let's see how that would work in practice. Let's say I have started to develop a time series for a product. And in the first period, I started out with a forecast of 10. I had to use my judgment because I knew nothing about this product. Demand turns out to be 12. Let's also assume I want to use an exponential smoothing model with an alpha of 0.3. So that means literally I'm going to put a weight of 0.3 on what my actual demand number is and 0.7 on what my forecast is. So when I end up forecasting for period 2, I'm going to take 0.3 times the actual demand in period 1 plus 0.7 times the actual, or excuse me, 0.7 times the forecast for period 1, and I end up getting 10.6. That's my forecast for period 2. All right? Now notice what happens. When I end up forecasting for period 3, I take 0.3 times 15, which is the demand in period 2, plus 0.7 times the forecast in period 2. But because the forecast in period 2 was made up of the original forecast and demand in period 1, these numbers in effect get rolled into the forecast for period 3, but with less weight. So what the exponential smoothing forecast does is it never forgets the past history. It just starts to weight it less and less as time goes on. And that's where the exponential aspect of the model comes into play. So look how this model is behaving. Demand goes 12, 15, 11, 9, 10, 8, 14, 12. So it doesn't seem to be an upward trend or anything, but there seems to be some randomness. So look how the model performs. It tends to kind of hover somewhere between 9.5 and 11.5, so it does take some bumps. So it seems to behave reasonably well, and I will tell you in practice they've examined how exponential smoothing models work in certain situations, and they seem to do very well. Now, one of the questions you may have is how do we determine what alpha will be? Why not 0.25? Why not 0.46? Well, the first thing I want to point out is that as individuals, we're not going to be picking alpha. It's very likely we're going to turn that over to a computer application which will pick an alpha that will result in a model that seems to fit past history very well. Let me say that one more time. Deciding what the alpha is going to be is something we're going to turn over to the computer logic, and it's going to try different alpha levels until it finds one that results in a forecast that seems to match past demands pretty well. We're going to kind of fit the model in effect. So that's one aspect of the alpha I want to talk about. The other issue I want to talk about is why we have different values for it. And to do that, I'm going to go to the forecasting spreadsheet that you all have. Okay, what I've set up here is I have a time series with 20 periods of demand, and you can see that plotted in the blue, and I have an exponential smoothing forecast resulting from using an alpha of 0.1. So to come up with a forecast for period 2, I took 0.9 times the original forecast of 10 plus 0.1 times the demand of 10, so no surprise I came out with 10. But because I have a very, very small alpha, this model tends to be very slow to react to changes in demand. Now look at the time series, the actual demands, and look at the forecast models. And I've got a question for you. Do you think this is an appropriate forecast model? Do you think we're picking the right alpha value or not? And you might say, well, hey, look, in period 11 here, demand went up to 20 and we missed it. And also in period 18 here, demand went down to 4 and we missed that as well. Well, the question we have to ask ourselves is how would we modify the model to do a better job? Well, let's try a higher alpha value. Let's suppose we went with an alpha value of 0.8. Is this model any better? Your initial reaction might be, yeah, the model looks better because it has the peak and the valley, but the problem is it's off by a period. So we still miss the forecast, we still miss the demand in period 11, but we really screw up in period 12 because we overreacted to what was random noise. Ditto here, we had a random drop and we overreacted in the model in the next period. So we made the model worse by making it overreactive. So the general argument is is if you have a model with if you have a demand pattern with a lot of random noise in it, then you want to keep the alpha level low. You want it to not overreact. Alternatively, what if I had a demand pattern that looked like this? Now what do we notice? When we had that big old bump in demand in period 11, it wasn't just random noise, it was indicative of a change in the underlying demand. And so in this case, what do you notice? The model reacts slowly, slowly. Eventually would get there, but obviously too slow to be of use to us. If we have a situation where we think demand is going to follow patterns like this, where big movements are indicative of a change in the underlying demand pattern, then we want a model that would react faster. And that's what I've done with the 0.8 for alpha. So the point is, picking the right alpha is going to be something that we're going to turn over to the computers, but generally speaking, if there's a lot of randomness in the data, keep alpha down. If there's not a lot of randomness and changes in demand means something, then alpha will come up, or should come up. Okay, and so again, we have a demand pattern here, we have an exponential smoothing forecast, and when we plot those out, we can see the smoothing effect going on. Now, part of the problem with a simple moving average and the exponential smoothing model, at least the way we define them, is that they don't consider trend. They only consider movements in the base demand. So if we actually want to have an exponential smoothing model, or I would say more generally a time series model that has a trend component in it, then we have to do something called double exponential smoothing. And in this case, we have to modify our formulas a little bit. We have an adjusted forecast, which now consists of a base forecast plus an estimate of what the trend will be. And the way that formula works is the adjusted forecast AF T sub T plus 1 is equal to F of T plus 1 plus trend T plus 1. And where do we get the forecast for period time T plus 1? We take alpha times the actual demand in period T plus 1 minus alpha times the current period's adjusted forecast. So it looks a lot like the basic exponential smoothing model here. The trend component, what's it doing? It's now taking a weighted average of the last period's estimate of trend and the difference between our unadjusted forecast for this period and the previous period. So it's almost like trying to say, has a trend increased or decreased? So the point is the model's looking at two things. Do we have a change in the underlying base demand? Do we have a change in the underlying trend? You could almost imagine a situation where you've got a trend going up like this, and we have a change in the base demand, which bumps it up one time, but the trend stays the same. Alternatively, you could have a situation where the trend's all over the place and the base demand's not changing. So the model's trying to figure out which of these two things are going on. It's best if we show this using some calculations. So keep in mind these formulas as we go to the next slide. And in addition, I have a spreadsheet that will do it for you as well. So you can actually go in and look at how the different components are calculated. So in this case, I have two different smoothing constants, one for the base demand to deal with the randomness and another to deal with the trend. So let's say in period 1, I start off with a notion that I think base demand is 27, but I don't have any trend. I don't think there's any trend in the data. Well, what if it turns out that the actual demand was 30? Look what happens. Okay, well, I thought the demand was going to be 27. It turned out to be 30. Maybe I do have some trend. What happens next time around? I come up with an adjusted forecast for period 2 of 28.44, but demand turns out to be 34. Okay, maybe I have more trend than I thought. So what you notice in this model, it starts estimating a trend in the data. It starts picking up on the fact that there does seem to be a trend in the data. You can see it here. Here's the actual demand. Here's the model. Now look what happens. Once we get up to about, I guess around period 10 or 11, demand starts flattening out. What do you notice in the model? Its trend component starts flattening out until finally toward the end of it, we have very little or no trend. The model starts pulling down. So you're seeing the dynamic nature of this exponential smoothing model. I just want to put it out there for you to appreciate these types of models are built into planning software, but they do a pretty good job of differentiating between changes in trend and changes in the underlying demand pattern. So they're fairly sophisticated. Now there's another way we can deal with time series, and that's linear regression. Linear regression can also be used for causal models. So if we talked about a very simple linear regression, what do I mean by that? I mean a situation where we have one predictor variable, or what I will call the independent variable, and one dependent variable, the one we want to predict. So we can use this for time series or causal modeling. It assumes there's a linear relationship between our independent variable and our dependent variable, and we can express it as such. The key in regression, obviously, is to figure out what the intercept term is and what the slope is. So let's say I have a set of data, and I've plotted different values for y associated with different values of x. I got paired data that I've plotted out here. What do you notice? Well, if you look at this data, and by the way, the data may not be arranged by time series. Who knows what the order of the individual observations were? We seem to see a downward trend, or I don't want to say trend. We seem to see a negative relationship between y and x. As x increases, y comes down. So we have a negative slope here. And in fact, what does regression try to do? Regression tries to fit the best line it can through that data. And I think if you remember your statistics lessons, they talked about fitting a line that minimizes the sum of the squared errors between where the actual points were in the line is. We're MBA folks. We're trying to fit the best line to the data we can. And so ultimately we come up with an equation, we come up with an equation where you tell me what x is, or what I think x would be, and I can use that to predict what my y value would be. Pretty simple, right? Now, that's simple linear regression. In some situations, we may see a nonlinear relationship between our independent variable x and y. Think about this function here. You ever seen something like this? Sure you have. You've seen situations where our independent variable increases and our dependent variable goes up, but not linearly. And in fact, if we see something that looks like this, the demand or the plot between x and y looks like this, we may think about fitting a nonlinear model where we take the natural log of x and regress that against y. So again, we come up with where we think the intercept term is, what the slope is, but instead of just putting in the straight x values, we regress the natural log of the x values against y, and that's a nonlinear model. Alternatively, a little bit more sophisticated is multiple regression. We have more than one explanatory variable or more than one independent variable. Once again, this is something you probably did in your statistics course. If not, I'm just trying to refresh your memory about where you might have seen this before, or I encourage you, frankly, to go into Excel and play with this stuff. Now, one of the things we have to deal with, even if we use a regression model, or even if we use a adjusted exponential smoothing model to deal with trend, we sometimes still have to deal with seasonality. So there's many ways to deal with seasonality, but it really boils down to estimating a seasonal index that is used to adjust the forecast up or down based on particular times of year. And I want to point out right now, seasonality doesn't necessarily mean spring, summer, fall, winter. It could be a particular 2-week period during the year, or it could be a month-and-a-half period, or whatever. But here's the idea. Seasonality index, as we're going to calculate it here, is it's going to be based on a percentage change in the base forecast. So let me show you how we might do it very quickly. Let's suppose we have a situation like this. I have 8 periods of data here. winter of '07 through the fall of '08. So I have 8 periods here, and I have the actual demand numbers there. So if I were to fit a regression model to this, what's my X variable going to be? My X variable is going to be the period, right? I'm going to use the period to predict demand. So I run a regression where the period is my X variable and the actual demands are my Y variable. So I end up with a regression equation that would look something like this. My estimated demand is going to be negative 18.57 plus 108.57 times the period. Where did I get those values there? I ran a regression, so it told me what my intercept term is. It told me what my slope coefficient for the regression line would be. So if I'm forecasting for period 1 then, I stick a 1 in here, I get 108.57, I subtract 18.57 from that, and it gives me my forecast of 90. And you can see it here. Do the math if you don't trust me. I put 2 in for this equation, it cranks out a regression forecast of 198.6 and so on, all the way down. Okay, so if I start looking at what the actual demands were and what the regression forecasts thought they would be, is this a very accurate model? Well, winter '07 doesn't look too bad, but I'm really off in the spring, and I'm really off in not only in the spring of '07, but the spring of '08, and I'm really off in the winter of '08. In fact, if you look at the winter of '07 and the winter of '08, in both cases, I have a negative forecast error, which means I over forecasted. Negative forecast error means the actual forecast was greater than the demand, 80 minus 90, negative 10. But on the other hand, if I look at the spring, in this case, I tend to be badly under forecasting. Now again, I'm doing this based on 8 periods of data. We'd want to have a little bit more information, but I'm just trying to make the point of how the numbers would work here. So let's say I look at this and I want to make some seasonality adjustments to make my model fit the data a little bit better. First of all, here I can see the graph between the demand and the forecast, and you can see I have some bumpiness, but in this case that bumpiness is not just randomness, it's seasonality effects. Okay, so how would I calculate a seasonal index? Well, what I would do is I'd go back to the data I had, and let's say I'm developing a seasonal index for the winter quarter. So for the winter of '07, actual demand was 80, the forecast was 90. So the actual forecast turned out to be 89% of the demand. Or I should say, excuse me, the actual demand turned out to be 89% of the forecast. In the winter of '08, the actual demand of 400 turned out to be 76% of the forecast of 524.3. So if I take the average of these two numbers, I get 0.83. Literally, I interpret that as for the past 2 winters, on average, actual demand has been 83% of the forecast. So you can see where we're going to go with this. I've now calculated a seasonal index for the winter quarters of 0.83. So what I'm going to do then is every time I forecast for the winter quarter in the future, I'm going to take the basic model, I'm going to plug in the period, but then I'm going to multiply it by 0.83 to bring the forecast down because I've tended to over forecast. More generally, the way the seasonal indices work is I take the base forecast and multiply it by the seasonal index, whether that is a number of greater than 1 or less than 1. If the number is greater than 1, that implies I'm trying to boost up the basic forecast. So it implies I've been under forecasting. But if it's lower than 1, which is the case here, I've been over forecasting. So again, let's look at all the numbers here and see if it makes sense. So what do we notice? Let's take winter '07. The actual demand was 80, the regression forecast was 90, the demand over the forecast was 0.89. In the winter of '08, actual demand was 400, the regression forecast was 524.3, the demand over the forecast was 0.76. When I took the average of the winter of '07 demand over forecast and the winter of '08 demand over forecast, I got 0.83. So I'm going to use that seasonal index every time I forecast for the winter. So how did I get the 74.3 here? It's really rather simple. I take the base forecast, multiply it by the seasonal index, come up with a seasonally adjusted regression forecast. Same thing down here for the winter of '08. I take the base regression forecast, multiply by the same seasonal index of 0.83, and I get my seasonally adjusted regression forecast. Now what happened in the spring? In the spring of '07, the demand over the forecast was 1.21. Literally, the demand was 20% higher, roughly, than the forecast. In the spring of '08, demand was about 14% higher than the forecast. So when I take the average of 1.21 and 1.14, I get 1.17, implying the actual demand on average was 17% greater than the forecast. And I just have a different seasonal index. Now I'm trying to pull the forecast up. Forecast basic regression model 198.6 times 1.17 gives me 233. Basic regression forecast down here for spring of '08, 632.9 times 1.17 gives me 742.4. So you see I've got different seasonal indices for each quarter, and they're repeated because I'm doing this for 2 years. And if you look at it, the model seems to fit the data better than it did before. If you want to look at it graphically, it looks like this. And you go, yeah, that's great. Congratulations, Dr. Bozarth. You've done a tremendous job of predicting what happened in the past. Well, that's not really what we're trying to do here. The only reason we spend all this time trying to fit the model to the past data is we are literally tailoring the best model we can given the data we have. So yes, I've got a model that seems to fit the past data pretty well, but that's because I purposefully tailored this model to do that. Do I expect the forecast to perform this well with future data? Not a chance, because once I start going into the future, I'm going to have data that wasn't used in building the model, but I'm doing the best I can. And so I would never go forward to my manager saying, I expect this model to fit the future data as well as it fits the past. But it's the best I can come up with right now. Makes sense? Think about it this way. If you ran this demand for a couple more years, you'd want to go back and recalibrate these seasonal indices, right? You'd have more data to build it off of. And in fact, if you remember from your statistics class, your professor would probably be horrified that we ran a regression on 8 data points. But all I was trying to do was fit a line to the data. Okay, so there's obviously a lot of strengths to time series forecast models. One of the things I haven't mentioned now is because they're relatively automated, we can launch time series forecast models for thousands of items. If you're talking about a Walmart or a Home Depot or a Lowe's, they've literally got hundreds of thousands of items to forecast for. So generally speaking, they're going to try to turn over forecasting to time series models, and they're only going to bring a human in when the models really perform very poorly and the computer applications can't make adjustments. So think about time series models as being very good, cheap forecast models when you have a lot of forecasts to do. The problem, the limitation with them is that moving average and exponential smoothing techniques really are designed to forecast only one period ahead. If you want to forecast for 12 periods ahead, you find out that if you have a basic moving average model, your forecast is not going to change. It's going to be the same for the next 12 periods. If you have an adjusted smoothing model, then it's going to assume the same underlying demand and the same trend per period. So the model's results tend to look boring if you try to take them out more than one period. So that's a limitation. Time series models assume demand patterns are time related. They can't anticipate the impact of changes such as adding or losing a major client, introducing an entirely new product or service, economic or regulatory changes. They assume everything's a function of what happened in the past. And we know while that may be useful for just building models, there's really other things besides what happened in the past that determine what the demands will be. So when that happens, we need to use a different technique. We need causal approaches or qualitative forecasting. So as I mentioned, causal models assume that demand is a function of something other than time. We already talked about the example of dollars spent on drought relief. Now what about the price of fuel? Well, we might argue that fuel tends to go up in price over time, but really a lot of the movement in the price of fuel is due to other things like economic conditions, tensions in various parts of the world, etc. So when we have causal situations like this, when we want to predict demand as a function of something other than time, we can use regression model again. But in this case, instead of having our independent variable be the time period, it's going to be something else, and we can have multiple independent variables. Example I like to think about is, let's say you run Lance's Catering, and you're trying to figure out how much barbecue to bring to the party. So every party you cater, people are going to eat a barbecue there, and barbecue is pretty expensive, so you don't want to bring any more than you have to, but you obviously don't want to bring less. So if you start to think about how you predict how much barbecue would be eaten at a party, obviously you're going to look at the number of people who are coming, right? That's an obvious independent variable that will drive how much barbecue is eaten. But you might also try to look at something else beyond that, not just the number of guests, but maybe how big they are. Now, how would you get information like this? Well, who knows? Maybe what you've done in the past is, let's say you have about 18 parties or so you've given in the past. You looked at how much barbecue was eaten, you counted how many people came in, but what you also did is you set up this nice little entryway to the party area where you surreptitiously weighed everyone who entered. So now you got two potential independent variables for explaining how much barbecue is going to be eaten. How many guests there were and what their average weight was. And together, I'm going to use both these variables to predict demand. So everyone see what I'm doing here? So first of all, let's look at this and suppose we just simply plotted out how much demand was eaten at the last 15 parties without considering the number of people or what their weight is. So if we plot it out as a time series, is that very helpful in figuring out how much barbecue is going to be eaten at the next party? Not really. I mean, it says, oh, well, we could have anywhere between 35 and 65 pounds of barbecue. So in this case, a time series model is not going to be a lot of help. On the other hand, instead of plotting the barbecue eaten versus the order of the event when they took place, suppose I plot out the barbecue eaten as a function of the number of guests and as a function of their average weight. Now, it's not completely crystal clear, but you can see, generally speaking, as the number of guests goes up, the amount of barbecue eaten seems to go up as well. But what this obviously isn't factoring in is the size of the people. So if we look here, again, we see a positive relationship between the average weight and the barbecue eaten. This one is not considering the number of people. This one's not considering their average weight, but together they provide a pretty complete three-dimensional picture of how much barbecue is going to be eaten. And in fact, when I run a regression, I get the following equation. I estimate that the barbecue eaten is going to be equal to 12.52 plus 0.15 times the number of guests plus 0.15 times their average weight. So how do I use this model? Well, if Lance is expecting 165 guests with an average weight of 150 per guest, I plug those values in, and I get an estimate of 59.77 pounds worth of barbecue. Now, if we were all undergraduates, here's what we would say. How much barbecue should I bring to the party? 59.77. But we're MBA students. How much barbecue do we bring to the party? And what you should say is something more than 59.77. It might be 70 pounds, it might be 65. It's going to depend on how confident we are in the estimates here. And so if you remember from your days of doing regression analysis, these are estimates of the coefficient estimates, right? And for each one of these, you usually get a 95% confidence interval of what the high and the low values are. Well, maybe what we do is, just to be safe, we put in the high estimate of the coefficient values and come up with something else. But in any case, my point is, even though you think they're going to eat 59.77 pounds of barbecue, you're going to take some safety stock. You don't want to run out of barbecue. People are going to get angry. Okay, so that's covering the quantitative techniques. The qualitative forecasting approaches come into play when there's little or no data available, or we have a hard time establishing a relationship between past events and future events. And some of the common approaches, like I talked about, are the life cycle analogy, consensus forecasting, and management judgment. The consensus forecasting approach is usually used for long-term strategic forecasting. The typical approach to consensus forecasting is you purposefully have different areas of the business who have different sets of knowledge, assumptions, etc., develop their own independent forecast. For instance, if I'm trying to figure out what the demand would be for a brand new product, I might have corporate marketing work on their forecast based on their understanding of competitive conditions, etc. I might have the analytics group build a model based on econometric data. I might even have the sales force build a model based on what they think they can sell out in the marketplace. But they all three would build their own separate models with different sets of assumptions. Then they would come together, each of those different areas, they would share their forecasts and the assumptions and the approaches they used. It's very unlikely they're all going to line up on a forecast. So after they share their information, the areas would then work independently to reassess their forecast, and hopefully over time you'll see a convergence around a final set of numbers. Now obviously, if I'm going to go through the consensus forecasting effort, it's going to be for a strategic big dollar situation. I'm not going to do consensus forecasting at the Home Depot for how many boxes of 6-penny nails I'm going to sell. I'm going to do this when I'm talking about launching a new product or service or whatever. It's very expensive, highly subjective, but again, we're trying to bring in the opinions of different experts. Now, Q2 forecasting. What Q2 forecasting does is it basically says, hey, if we have any data available, let's at least try to develop a preliminary forecast. Even if it's not going to be exactly correct, but it gives us a baseline to start from. So for instance, think about the economic turmoil that we faced over the past 4 or 5 years. We might try to develop a forecast of what we think our business levels are going to be based on what we've seen for the past 2 or 3 years. And we'll use that as a preliminary forecast, maybe like a very simplistic time series model. But then we're going to take that and we're going to look at some other factors. Maybe we say, hey, maybe the economy is improving, or maybe it's not. Maybe our competitors are launching similar products or whatever. And we take the raw set of numbers that are, or I wouldn't say raw set of numbers, but the preliminary forecast, and we apply a qualitative filter on it to come up with a final forecast. Maybe we end up bumping up our preliminary forecast by 10%, or maybe we start bringing it down the next 6 months. But the point is, we're trying to make the best use of quantitative and qualitative techniques. Now, I want to go back and talk about the life cycle analogy approach real quickly. The whole idea behind the life cycle analogy is, let's say we're in a business where we have launched products in the past and they have a very distinctive life cycle. Let's say we're in the high-tech industry where there's a quick growth, there's a maturity phase in demand, and then demand tends to drop off. If we've seen an approach like that before, then we can try to fit that to future demand forecasts. If we're talking about new products, for instance, we may anticipate from what we've seen in the past that there'll be a 3-month growth period in which demand will triple and then demand will top off and then come back down. So we can use that kind of qualitative technique to get estimates when we see distinctive life cycles in the products or services we launch. All right, so let me move back forward through the Q2 forecasting to the lesson summary. So again, if we've got data available, then we're going to try to fit time series or causal forecasting models, at least as a first step. If there's little or no data available, then we're going to have to depend on qualitative forecasting, whether that involves a life cycle analogy, consensus forecasting, or simply managerial judgment. There's very few situations where we have absolutely no data available and we do pure management judgment. More likely, we're going to have some data available so we can develop some kind of a preliminary forecast where we then apply our filter. Okay, so with that done, let's get into a discussion of how we measure forecast accuracy. To keep it simple, there's really two main types of forecast model error that we are concerned with, and that's bias and absolute error. Bias basically is telling us, does the model tend to under or over forecast, while absolute error is concerned with the magnitude of the errors we make, regardless of the direction, regardless of whether we're under or over forecasting. So let me give you an example how this works. In period 1, let's suppose our demand was 11, but our forecast was 13.5. So if we calculate the forecast error, we take the demand minus the forecast, and we get negative 2.5. So in this case, the negative implies that we over forecast. And this is just like we talked about before. Now, absolute percentage error, what does this say? Well, absolute percentage error is calculated by taking the absolute value of demand minus the forecast. By taking the absolute value, we don't care about the direction of whether we under or over forecast, but how big it was. So we take that absolute value of the forecast error and we divide it by the demand and multiply by 100%. So it literally is saying here our forecast error represented 22.7% of the actual demand. And that gives us an idea of the magnitude of the errors we're making. In period 9, once again, we over forecasted, and the magnitude of the error was significantly higher in this case. Actual demand was 9, absolute value of the forecast error was 4. So I've gone ahead and run through that for all 6 periods here, and make sure you're comfortable with how the calculations are done. Once I've calculated the forecast for these 6 periods, and I've calculated the absolute percentage error, I could take a straight average of these and figure out what the mean forecast error and the mean absolute percentage error are. So literally, I took the mean of the forecast errors. It turns out to be negative 0.33. The way I interpret that is, on average, I'm over forecasting by about a third of the unit. If I look at the absolute percentage error, or mean absolute percentage error, on average, the absolute value of my forecast error is 21.7% of the underlying demand. So that's pretty significant, but the question is, can we do better? In a lot of cases, that may be the best we could do. So the reason we measure bias in terms of MFE and mean and absolute error in terms of MAPE is so we can get an understanding of how well the model is working versus what it did in the past versus what maybe a different model might do. Let's go into this in a little bit more detail. So let's suppose I have identified bias in my forecast model. It tends to either lead or lag the actual demand. When we see situations like this, it's usually because we're using the wrong forecasting technique. For instance, in this particular case, you can see the actual demand here in blue. You can see a simple moving average model, which doesn't have a trend factor in it. And so a simple moving average model is always going to lag demand with a trend. And in this particular case, by going to a trend adjusted forecast, we could significantly improve the bias or take out the bias of the forecast model. So this is an example where we can make the correction pretty quickly. And again, think about this. If you have a model that tends to over forecast by 0.5 units and it does that consistently, well, either switch to a model that gets rid of that bias, or maybe we add or maybe we adjust the forecast by 0.5 units to take out that bias. So bias isn't usually the most difficult thing to deal with. The more difficult thing to deal with in a lot of cases is the absolute size of the errors. And let me show you a demand pattern here with a forecast model fit to it, and we can talk about it a little bit, but we'll come back to this in a moment and I'll give you more information. But in this particular case, what do you notice here? I have demand bumping around at about 10, except for 3 periods. Demand seems to double. around 20, 21, 18, then it comes back down, and then I have another bump up to 15. So look what my model does. My model throughout this period of time is basically looking at for the first 9 periods or so, is basically looking at the changes in demand as being noise. Now, when I start to get the 3 periods of high demand here, my model starts to come up, but relatively slowly. So I have some significant forecast errors in those 3 periods. Then the model starts to come back down again. And once again, we kind of miss this demand, but I'm not sure we could really capture that. So if I go back over this set of data here, and I measure the mean absolute percentage error across all these periods, it turns out to be 21%. But as you can imagine, that mean absolute percentage error really is being driven by the bad forecast errors in these 3 periods. In fact, we're 9,800 units short in period 1. That'd be a mean absolute percentage error of what? About 100%. Okay. Now, we talked a little bit about bias, we talked a little bit about forecast error. So what? Why is it important to have an accurate forecast? Well, I think you understand why forecast accuracy is important, but let me put a numerical example on it. When demand is unknown, decision makers have to make a trade-off between shortage cost and safety stock capacity cost. We can explicitly show how these costs decrease as forecast accuracy increases. In other words, you give me a more accurate forecast, in a lot of business situations, I can reduce inventory or capacity as a result. The information has value. And it's a general truth in management. We can always substitute resources for knowledge, but usually knowledge is cheaper. So let me give an example how this would work with a single period inventory model. And you've seen this before. We did an example of a single period inventory model when we did the leapfrog case study. But here's the scenario. Suppose we're in the military and we're trying to figure out how many XYZ repair kits to ship to Afghanistan to support the troops. If inventory runs short of these XYZ repair kits, they can be quickly flown in, but at an additional expense of $800 per kit. So in other words, we really don't want to have to fly in extra ones because it adds to the cost. On the other hand, at the end of the engagement, any repair kits left over that aren't used on repairing the XYZ have to be repatriated at a cost of $200 per kit. We're not going to leave them in the field. So we have a situation where ideally we'd like to ship exactly the number of kits we need over, no more, no less, but that's not realistic. So we have to figure out, do we want to err on the side of having too many kits there or too few? And so we start thinking about the target service level. Well, the target service level is determined by taking the shortage cost divided by the shortage cost plus the excess cost. So if we're short, it costs us an additional $800 to ship a kit out. If we have too many, it costs us an additional $200. So generally speaking, shortages are much more expensive than excesses. And in fact, we figure out that the target service level is going to be 80%. Put another way, if we put enough inventory in the field to meet the 80th percentile of demand, then we will have balanced off the shortage cost, the expected shortage cost versus the expected excess cost. Now let's assume for a second that we have no bias in the model and that the forecast errors are normally distributed. So if we had a situation like that, I could show you with a little bit of time that given an expected demand level, I could figure out what forecast we would have to ensure that demand was had only, for instance, a 20% chance of actually being higher than that. So in other words, I could tell you what the expected demand level is, and I could calculate the 80th percentile of demand or the 95th percentile of demand based on my understanding of what the forecast errors are. This again assumes we're in a situation where there's no bias in the underlying model and the forecast errors are normally distributed. So with that set of assumptions, let's go back and consider our target service level. If the expected demand level for these XYZ repair kits is, let's say here, What the target service level says is we really need to establish our inventory level at the 80th percentile. And how much higher this is than the expected demand level is going to depend on the accuracy of our forecast model as measured by the forecast errors. So the difference between the expected demand level and this 80th percentile is what we call safety capacity or safety stock. So this is all due to variability as reflected in the current forecast model. Now let's change it around a little bit. Suppose we come up with a forecast model that has much smaller forecast errors. It's still an unbiased model, but it's much, much more accurate. What's this going to look like? Well, what we're going to see then is that we still have the same expected value, but because the forecast errors are much, much smaller, then the 80th percentile of expected demand is not going to be that much greater. So in effect, what's going to happen is we'll have reduced the safety capacity required solely by having a more accurate model. Let's put it this way. What if there's absolutely no error in the forecast model? We could predict exactly how many XYZ repair kits would be needed. Then we wouldn't even need to worry about this target service level. We'd ship exactly what we need and we'd have no worry about shortage or excess cost. So my point is, going from here to here, from here to here, you see the shrinking in the safety capacity. That's a real savings that we can tie to improvements in forecast accuracy. So literally, if I was doing this in a real business, if I could say, hey, I'll bring your forecast errors down by 20%, what's the impact going to be on safety stock? I could calculate it out. Okay, so that's a little bit of the background. Again, we've talked about the forecasting imperative. We've talked about some different approaches. We've talked about how we measure forecast error. Now I want to get into the fun issue of the forecasting business process, how we as people use it. In reality, we can have great numbers. We can have done all the things right, but if we do not communicate and use the forecast appropriately, then things are going to fail. So the question we have is, when we forecast, do we track and report forecast model accuracy? Do we differentiate between assignable and unassignable demand variances? That is, do we go back and try to learn based on what happened? Do we involve key partners into the forecasting and planning process? One of the things we'll talk about in a few slides is the whole idea of why we forecast in different organizations when we're both going to use the same forecast to plan our activities. Finally, do we manage and improve the forecasting process like any other business process? I just showed you the value of forecast accuracy with the XYZ repair kit. So why don't we think about having Six Sigma projects that improve forecast accuracy? There's obviously a cost savings involved. So what happens when the forecasting process is broken? And I'm not necessarily talking about whether the numbers are good or not, but whether they're being used appropriately. Well, when the forecasting process is broken, users both within the firm and outside the firm lose faith in the forecasting process and the numbers generated. The result is everyone starts to develop their own forecast. So you have redundancy as well as uncoordinated forecasting and planning efforts. Marketing goes off and does their thing, operations does their thing, purchasing does their thing, and then finance comes in with a whole different set of numbers. Complete chaos. Other things you see happen is individuals start substituting orders for demand when planning. So in other words, if I'm a decision maker and I've depended on marketing's forecast and I've been screwed over several times for it, I may just say, look, I'm not going to do anything until I get an order. What else do you see? When the forecasts become crazy, people try to protect their areas through redundant safety stocks and capacity. If the forecast isn't very helpful, the only way I can protect myself is to make sure I have excess materials, capacity to buffer myself from that uncertainty. Let me give you an example of these types of failures. Example 1, failure to track and report forecast model accuracy. So in other words, when I'm communicating a forecast to someone who has to make a decision about, for instance, safety stocks or whatever, they need to have some idea of not only what the underlying forecast is, but what is the expected accuracy of that forecast. So maybe I could tell them the forecast is 200, but with an expected standard deviation of 25. So they could use that to plan the target service level. Instead, what you see in business is someone will say, well, assume the forecast is 250. The problem is that's not the same thing as telling that the forecast is 200 with a standard deviation of 25. By saying 250, I've in effect made the safety stock decision for them. You get what I'm saying here? Imagine this, if I'm sales and I tell production, or if I'm sales and I tell logistics that the forecast is 200 with an expected standard deviation of 25, then the logistics folks can use their knowledge of inventory cost and practices to determine what's the appropriate safety stock. But if sales just says the forecast is 250, then they've taken out all the decision-making capability from the logistics folks who should know how to strike the best balance between safety stock cost and demand requirements. So what you see in a case like this is when I get a single number like this, I start wondering what's included in that. Maybe I need to build something more than that or order something more than that to protect myself. So what you see is uncertain about what the real forecast is. The folks who get this number will either ignore it or modify it or depend on actual orders for their planning purposes. So point number one, not only share the forecast, but share measures of forecast accuracy with the people who are using the forecast so they can understand the risks involved. Another example of a failure in the forecasting business processes is a failure to differentiate between assignable and unassignable demand variances. This should look familiar. This is what we had a few slides back. Now, I'm going to talk about this in terms of the context of the product. This is portable generator demand, those gas-powered generators everyone gets at Lowe's or Home Depot. So what I have right here is what we would call unassignable random variation. Now, what if I told you, though, that these 3 peak periods of demand were due to a marketing promotion, while this peak was due to a storm-related power outage? So in this case, we had people buying portable generators because they're on sale. In this case, we had people buying portable generators because they had a power outage and they wanted to protect their homes. So if I know that information, how can I use that to come up with a better forecast? Well, recall that the old forecast model was off by 9,800 units in period 11, and as a result, the model had a MAPE of 21%, or mean absolute percentage error of 21%. If we had told the supplier to anticipate a marketing promotion in these periods, what might they have done? And in fact, suppose we didn't tell them. How do you think they'd react to learning periods 11 through 13 could have been anticipated for planned for? They're not going to be very happy, right? So there's a big distinction between this bump and this bump. We can anticipate this. It's assignable variation, but we can also anticipate it. This is assignable variation, but we can't anticipate it. So what I've done now is I've taken what was the forecast model before, but maybe someone looks at this, a planner, and says, look, we're going to have a promotion in periods 11 through 13 that typically bumps up demand by 100%, so maybe we bump up our forecast by 100%. Look how much better the forecast model does just based on that adjustment here. And again, we're adjusting here because we can anticipate this bump up in demand. Now this improves the model's mean absolute percentage error to 10% versus 21%. Now we're still off in period 18, but there's nothing really we could do about that because that's an unanticipated event. Question is, how do we deal with this then? Well, the way we deal with that is maybe we have shared pooled safety stocks across multiple stores or regions, but it's not the same as here where we could have anticipated the bumps. When we can anticipate the bumps, we build it into the forecast, or bumps or troughs. When we can't anticipate it, then we need to come up with some other mechanism to deal with that kind of risk. Let's get a third example, and this is one of my favorite examples. This was based on a company I did some work with here in a triangle, and they were a telecommunications company. And here's the situation they have. And let's just look at the numbers for a second. What do you notice? 4 quarters of data. These are the forecasts in millions of dollars. And here's the actual demands. And these numbers, by the way, are based on the company, but they're proportionally correct, if not correct, in actual dollar amount. What do you notice going on here? Percent forecast error, 27%, period 1, 21% in period 2, 33% in period 3, 24% period 4, and we're always badly over forecasting. In fact, they would have been better off, frankly, using the last period demand as a forecast for the next period. So how could they have screwed this up so badly? Were they dumb? No, they weren't dumb, but here's what was happening. Someone would develop an initial forecast. Let's say the initial forecast in period 1 was $100 million. What was happening then is they take that $100 million and various managers who didn't understand how the forecasts work insisted on adding firm customer orders on top of the forecast just to be sure the resources were there. So in other words, at the plant, they were planning $100 million worth of production, but someone says, well, we're almost certain to get this order from the Billy Bob company, so add the $25 million on top of that. The problem is that's not how it works. If the forecast is $100 million and a firm order comes in for $25 million, that firm order comes out of the $100 million forecast. It's not added on top. So imagine if you're the plant manager here and you've seen 4 quarters worth of data like this. You've got to be depressed. You know these forecasts are inflated, so you're ending up making inventory that you're not going to be able to sell. But if you don't make it, you're going to be in trouble. So you're damned if you do, damned if you don't. So how do we get around this trap? And this is not a trap driven by bad calculations. It's a trap driven by bad use of the forecast. Well, what it would require is someone to explain firmly and hold to it that any firm orders should come out of the forecasted demand, not added on top of it. But it's something this company couldn't get their arms around. So they ended up overproducing, stealing production from actual orders to make stuff that wasn't needed, excess inventories. They were actually working overtime to make products that wouldn't be sold. It was just really a real problem. So what are some of the tactics to improve the forecasting process then? 1, track and report forecast accuracy to all affected parties. So those people who have information about how to set proper safety stocks or how to establish trade-offs between excess capacity and demand, they have the information they need to make intelligent decisions. 2nd, communicate business conditions that may result in assignable variances. If you're in private industry, that means sales or new stores. And if you're in things like defense, if you're going to have a major deployment or withdrawal, that's going to have an impact on demand. Build that into the forecast. Continuing with this, push towards shared forecasts. And shared forecasts are the linchpin of sales and operations planning and collaborative planning, forecasting, replenishment, which we're going to talk about next. Finally, measure and improve the forecasting process itself. The criticality of forecasting often makes it an ideal candidate for business process improvement efforts. Everyone can see the benefit of it. Now let's talk about sharing the forecast. Later on in this course, we'll talk about sales and operations planning. And sales and operations planning is something that's done monthly to reassess the direction of the business and to make sure that marketing, operations, purchasing, HR, and finance, all the functional areas are on the same page in terms of the level of business. But it starts every month with demand planning, reassessing what the demand is going to be. In effect, re-looking at our forecast numbers. And based on those forecast numbers, then we plan how we're going to meet the forecast. Then we resolve any differences between supply and demand, between operations and marketing, in what's called a pre-sales and operations planning meeting. For instance, marketing may want us to work overtime to make additional products. Operations may have an issue of whether they have the budget for it, but they try to work out those differences. And then what you do is you go in and meet with the executives once a month to either approve the adjustments to where the business is going for the next month, or make decisions that can't be dealt with at lower levels. Think about sales and operations planning almost as if you were like driving to New York from Raleigh, North Carolina. When you're driving from Raleigh to New York, you're adjusting the steering wheel every couple hundred yards, right? But you're not making big adjustments. That's what sales and operations planning does, but it's doing it on a monthly basis. By reassessing the forecast every month and keeping on top of this, we end up making small changes here and there, but no one's really surprised. Okay. Now, collaborative planning, forecasting, and replenishment is different than sales and operations planning because sales and operations planning is within a business. Collaborative planning, forecasting, and replenishment is talking about relationships between supply chain partners. The traditional link is between a manufacturer and the retailer who sells their products. And there's a lot that goes on with CPFR, so let me give you the high-level overview. Let's say you're Walmart, and Walmart is the retailer, and you're Procter & Gamble, who's a manufacturer. So Procter & Gamble, you can imagine, is a huge consumer goods producer, and Walmart's a huge customer. So what they might do is say, look, rather than each of us develop separate forecasts of what we're going to sell of your product range, why doesn't Walmart and Procter & Gamble get together and develop a single forecast of demand for Procter & Gamble products? That way Walmart has an idea of what they're going to sell, Procter & Gamble has an idea of what they need to produce. Sounds pretty simple, right? So they agree to enter this collaboration arrangement. They agree to share joint business data. So for instance, if Walmart is going to have a sale on Procter & Gamble products, or if they're going to open up new stores or whatever, they let Procter & Gamble know that so they can anticipate it and build it in the forecast. They work together as a single integrated team to develop one set of forecast numbers. And those forecasts are not only used to plan tactical activities, they're actually used to execute orders. So sales forecasts eventually turn into orders, orders are generated, orders are filled, and if there's any exceptions that happen in terms of delivering the products or whatever, then they work together to resolve those differences. But it's really like Walmart and Procter & Gamble start working as a single organization. Now, obviously, there's some organizational dynamic issues you have to deal with here, but it's truly a partnership. Now, let me give you a little bit more appreciation for how CPFR might work at the very detailed level. So don't freak out here. But let's say I'm retailer X, and we'll say it's Walmart to put a name on it. And I have the forecast for cases of, I'm trying to think of a Procter & Gamble product. Pampers diapers. So here's the forecasted demand for cases of Pampers diapers. And what do you notice about this forecast? I think I'm going to sell 1,000 cases in week 1, 1,200 cases in week 2, 1,200 cases in week 3, 1,800 cases in week 4. Is that because the babies are becoming sicker or they're eating more food, they need more diapers? No, maybe I'm having some special, some sale. So I'm going to be pushing Pampers in week 4, and then demands will come back down. This is the shared forecast between Procter & Gamble and Walmart for this product. Now what's happening here? Well, I'm using my inventory information, my expected forecast, to anticipate what's going to happen to my inventory levels of Pampers. So let's say I'm starting the week with 2,800 cases of Pampers diapers. I think I'm going to sell 1,000. That's going to leave me with 1,800 cases of diapers. What happens in week 2? I start week 2 with what was left over in week 1, 1,800 cases. I think I'm going to sell 1,200. That would bring me down to 600 cases, except I want to have 3,000 more cases arrive. So I'll end up with 3,600 cases of diapers. So I'm keeping a little bit of extra inventory here. I don't want to run out of diapers. 3,600 minus 1,200, I think I'm going to end up with 2,400 diapers in week 3, and so on. So I can see what the inventory levels are going to look like at the end of each period. Now what's happening here? Remember, in week 2, I anticipated receiving 3,000 diapers at the Walmart distribution center. Well, for that to happen, I have to release an order, let's say the week before, from Pampers. So I use this information at Procter & Gamble to identify when I need to make shipments. Ship 3,000 in week 1 so it gets there at Walmart in week 2. Ship another 3,000 in week 4 so it gets there in week 5, etc. So what you see is all the activities are tied to a single forecast. I'm making shipments based on the forecast. I'm not setting stuff before it's needed. Now, I got this weird thing called the line of visibility between plans and orders. And what I mean here is anything beyond 3 weeks in this case is simply a plan. I'm not committed to it yet. So if I have a shipment showing up here in week 4, I'm planning on shipping that, but I haven't committed to it yet. On the other hand, as soon as I get into the next 3 weeks of activity, anything here is a committed order. So what it does is it allows flexibility for things to change in weeks 4 on out, but within the next 3 weeks, I'm pretty much committed to what the plan is here. So to summarize, the downstream forecast are used to plan upstream activities. Here's the downstream forecast. Here's the upstream activity. I can size the safety stocks rationally and position them where I want them to be in the supply chain. In this case, I'm keeping the safety stock at the retailer. I could just as well bring the safety stock back to the distribution center. And supply chain partners trust the forecast and work to improve the process. Obviously, there's more to CPFR than this, but I'm trying to give you an appreciation for how the linkages might work. Okay, so to summarize this last lesson here, generating a good set of forecast numbers is great, but it's not sufficient. We have to share forecast information, we have to integrate the forecast into planning and control activities, and where appropriate, make the business case to improve the forecast. Certain business processes such as sales and operations planning and CPFR, or collaborative planning, forecasting, and replenishment, provide a framework for sharing and integrating those forecasts. And Six Sigma and other process improvement methodologies can be used to improve the forecasting effort. Now there's some related readings. If you're interested in CPFR, I encourage you to go to the 2 links I have here and you can find out a lot more about it. It's really a well-developed set of business practices. If you're interested in sales and operations planning, or you want to try to maybe roll it out in your company, then I encourage you to look at the How-To Handbook by Wallace and Stahl. We also talk about sales and operations planning in the course textbook.